right? If we're reviewing Lewis structures here, we've counted our valence electrons. Do you remember the two ways that we can represent electrons? How do we show electrons? We can represent them two ways. Okay, we can represent them with a bond. That's a line that represents two electrons, right? One from this atom and one from this atom, essentially. And then what's the other way we can represent electrons? With a dot, right? And specifically, we like them to be in pairs, right? Those are called lone pairs. And it's just with a dot that looks like that, a set of dots that looks like that. Okay, so we could represent electrons with bonds or pairs. And so we'll get through that as we work, okay? So carbon is going to be our central. And remember, we treat each one like it has four sides of the box, okay? So we're going to put a chloride on each side. Chloride, all four around. That's step 2. That's our skeleton. Okay, we knew carbon needed to go in the middle because that's really our rule about it. If we have carbon, it goes in the middle. And even if we weren't following that particular rule, carbon still came first in our molecule. So it goes in the center. All right, the last step is simple but complicated, right? We're supposed to fill in our electrons. That could be really easy or it could be complex. So this is the step that is the trickiest, okay? But let's go ahead and start doing it. Remember, I kind of gave the advice last time that as we're filling in electrons, the first thing we do is bond from the central atom to all of the outer atoms. That's step 3A, if you will, okay? By doing that, I've used up 8 electrons, which means I have 24 electrons left to represent, okay? So once we've done that initial bonding to each of our outer atoms, my advice was to fill the outer atoms first and work our way in. Right? Work outside to inside. So we're going to put electrons on our outer atoms. Do we just spread them out like this? Or how do we do it? They need to be in pairs, exactly. So we're going to put 2, 4, 6 electrons on that chlorine. Why did I decide to put 6 on chlorine there? Why did I put 3 lone pairs? That gets us to 8, right? 2, 4, 6, and then this shared pair right here gets us to 8 for that chlorine. So that's why I chose that. So I'm going to do the same thing essentially for all of my chlorine atoms. They're all going to get 3 lone pairs. That gets us to a place of complete octets for each of our chlorine atoms. And I did that. I put on 6 electrons 4 times, so that used up all 24 of my electrons, didn't it? Okay, and so now I've put all my electrons on my structure. I don't have any more or any less to work with. So I'm going to double check. This chlorine, does it have a full octet? Yes, 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 yes. And then I'm going to check my inside atom. Carbon has 2, 4, 6, and 8. So that is a complete and valid Lewis structure. Everything has exactly what it wants to have. Okay? Very good. Tell me what questions we have here. Okay, I'm going to have a sidestep for just a second, and I'm going to give you a table of information, a kind of a graphic organizer of preferences for atoms, preferences for these different types of atoms. Okay, so I want us to look at this in just a minute. I'm going to draw this table, and I'm going to recommend that you have this table in your notes as well. I will also eventually put it up on the board. Maybe you guys saw it when our other classes were working here, but I'm going to make us a table here of preferences. Okay. So I'm going to start with, we're going to draw out this table here. This is the group. This is the number of bonds they like. And this is the number of lone pairs they prefer to have. Okay? So in carbon's group, elements that are in carbon's group have how many valence electrons do atoms in carbon's group have? Carbon, silicon, germanium, they have 4 valence electrons because they're in group 4, okay? So I'm going to kind of draw those dots on here just because it helps us give a visual. And carbon's preference, just like silicon's preference and germanium's preference, but carbon specifically, carbon's group, they prefer to have 4 bonds and 0 lone pairs. It wants every one of those valence electrons to be used up in a bond. That would make carbon the happiest. Okay, because it contributed 4 electrons, and each of those electrons is being used up in a bond. So if you look over at the example we just did, right, here is carbon's 4 electrons, and they're all being used in a bond, aren't they? Right, so that makes carbon really happy, just like that. Agreed? Okay, so that's carbon's preference. The next group over has nitrogen at the top. So we're going to talk about nitrogen's group. Actually, I'm going to draw. We're going to talk next about nitrogen's group. Nitrogen's group has 5 valence electrons. So it looks like this. 1, 2, 3, 4, 5. So nitrogen's preference is to have 3 bonds with 1 lone pair. Right? If we're looking at nitrogen, we're going to see this bond, bond, bond. Right? That's nitrogen's preference. Because there's its 5 electrons that gets to stay close to it. Yes? Okay. So maybe we're seeing a pattern here. We'll see. The next element group is oxygen's group. Oxygen has 1, 2, 3, 4, 5, 6 valence electrons. Any guesses on how many bonds it wants?
2.
2 bonds. And how many lone pairs do you think it wants? 2, right? Do we see that, how that works? Okay, so this gives us really some power in speeding up our Lewis structures if we know preferences. We're also able to really get ourselves into a situation where we can find out the most valid Lewis structure quicker, right? By being able to satisfy these preferences. Because there's a lot of way we can arrange the atoms, but they won't all be preferable. They won't all be what actually happens with the atom, okay? So the next one over is fluorine. It has 7 valence electrons. What do you think its preferences are? 1 bond and 3 lone pairs. I would agree, right? 1 bond and 3 lone pairs. And again, this goes for every atom in that group, which includes chlorine, doesn't it? So come over and look at what chlorine had. 1 bond and 3 lone pairs, right? That's its preference because how many did it bring to the table? How many valence electrons did chlorine contribute? It contributed how many? How many valence electrons did each chlorine contribute? 7, right? So if you look at chlorine, here's 1, 2, 3, 4, 5, 6, and 7, right? It's getting to keep its electrons close to it, right? And then just share in another one. Do we see that why that's preferential? Yeah. It's not having to give away electrons to balance things up. It gets to keep those close. So that's why these preferences are developed, okay? And then the last group would be like neon's group. And how many valence electrons do they have? They have 8, right? So their preference is to have no bonds and 4 lone pairs. They don't want to bond with anybody, right? And we know that. So tell me, does that table kind of make sense for us? I'm going to put this up on the board so it'll be visible for us all the time, but this is a way for us to really, really dive into what do atoms want to happen. And that's typically how they orient themselves when at all possible. So as we work through Lewis structures today, I want you to keep this graphic organizer in the back of your head that I want to try to get to a place where oxygen has 2 bonds and 2 lone pairs, right? I want to try to get to a place where carbon has 4 bonds, things like that. Okay? All right, questions we have. Okay, so we're going to look at H2O. First is to count the valence electrons. All right, count valence electrons. So hydrogen each gives us 1. There's 2 of them. And oxygen gives us 6. That gives us a total of 8 electrons. All right, so tell me here, which one is going to go in the middle? Yeah, that's okay. It's tricky because hydrogen comes first here, doesn't it? So we kind of said, well, the atom that comes first is going to go in the middle, but that can't be true for hydrogen. So it's going to be oxygen, and we're going to spread out hydrogen on either side. Next step is to bond and start filling in electrons. So I'm going to bond them. That's used up 4. That leaves me with 4 left. But here again, we're not following our advice of filling outside in because why can't I put electrons out here on hydrogen? Is hydrogen allowed to have those things? No. It is not, right? So where do those lone pairs need to go? They need to go on the oxygen, okay? And we'll talk about where they technically get placed a little bit later in the chapter, but both of those lone pairs need to go on oxygen because hydrogen is happy, right? It has its bond. And look at our preferences. Did oxygen get its 2 bonds and 2 lone pairs like it wants to have? Yeah, it did, right? 2 bonds, 2 lone pairs. Okay, so again, before I finish my molecule, I'm going to go check, did I use 8 electrons? And I did. 2, 4, 6, and 8. And then I'm going to check, is oxygen happy with its octet? 2, 4, 6, 8. Yes, and hydrogen's good to go. Okay, so these simple molecules they follow all the rules. Okay, let's skip over, and you can be writing on this sheet. I hope you are, okay? Let's skip over to NCl3. Okay, what would that one be called?
Nitrogen trichloride.
Mm-hmm. Yep, nitrogen trichloride. Okay, so NH3. Let me move down a little bit. Can you still see that table up there? Okay, NCl3. Nitrogen gives us 5. Chlorine gives us 7 each, so times 3. 21 plus 5 is 26 electrons. What's the one thing that you're noticed so far about our valence electron numbers? They have to be even. Has to be an even number. So if you get an odd number out of that valence count, that means something probably went wrong with our math. Why does it have to be even? Because our electrons need to exist how? In pairs, right? Either in a bond or in a lone pair. So they have to exist in a pair. All right, so let's keep going here. Nitrogen's going to go in the middle. Chlorine, 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 right? We've done step 1 and step 2. We've added our valence electrons and built the skeleton. Now we're going to bond, bond, bond. That uses up how many? 6. So I've got 20 electrons left. How many lone pairs will I put on each chlorine? Each chlorine. How many lone pairs will chlorine get? 3 on each one, right? Because that's going to fulfill the octet. So 2, 4, 6, 2, 4, 6, 2, 4, 6. So I put 3 lone pairs on each chlorine. So I've used up 18 electrons. Would we agree about that? So that leaves me with 2 electrons left. Do we see a spot for those to go? Where at? On nitrogen. Okay. And we maybe talked about this a little bit last time, but where we put the lone pair is not super important right yet, but it just needs to go in a gap. Okay. So it can either go here or it can go here or it can go here. Okay. What it cannot do is it cannot exist as a single, right? That's not a lone pair. They're separated there. It also cannot exist in the same domain as the bond. It needs to be in a gap somewhere. So we're just going to put our lone pair on somewhere and leave it there. 3-dimensionally, it looks a little bit different. We'll get to that later, but that's where we got to be for our structures, okay? We're going to check, does chlorine have octets that are full? Does nitrogen have a full octet? Yes, right? Does each one get their preferences? Yeah. So everything's happy and dandy. Okay, so for these simple molecules, things work pretty well. Okay, let's get down to one of these in group 3 called a polyatomic ion. And I actually want to try... Yeah, let's go ahead and just do PO4 minus 3. Okay, we're going to dive into a lot of intricacies here. Okay, so we're going to go PO4 minus 3. All right, let's count our valence electrons. Phosphorus gives us 5. Oxygen gives us 6 times 4. But how do you think this charge affects our valence count? We add electrons in, right? Because we have 3 extra negatives, right? We got to think about our charge like that. We have 3 extra negatives, and negatives are electrons. So we have 3 extra electrons, so we are going to add that to our total. The reason those molecules need extra electrons is to satisfy octets. That's the reason those have to be there, okay? So we're going to go ahead and add those up. So 24 plus 8 is what? 32. 2 electrons. Did I do that right? 24 plus 8 is 32. Okay. So how about our central atom here? What do we think it's going to be?
Phosphorus.
It's going to be phosphorus. I'm going to have 4 oxygens around the outer edge. I'm going to bond, 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 bond. Out of my 32, I've used up 8, which leaves me with 24 electrons. So we're gonna get a little more complex here. I'm gonna show us some extra things that are happening. Yeah, we're gonna go ahead and just get right into it. How do we feel about the simple ones? Are we feeling confident with that? We're ready to add a wrinkle in here? Okay, very good. So I'm not gonna just show you the basic one. I'm gonna show you, we're gonna amp it up a little bit here. Okay, so my next rule is to fill the outside. So we're gonna go ahead and complete the octets for each of my oxygens. Okay, complete the octet for all of our oxygens. Not coincidentally, that uses all 24 electrons, right? I put on 6 electrons times 4 oxygens. So I'm out of electrons at this point. I have nothing left. No more can be added or subtracted from our system. Okay, now does this Lewis structure seem valid? Phosphorus has complete octets. Oxygen all have complete octets. Everything seems nice and dandy, doesn't it? However, we're going to start to develop the understanding of the difference of valid structures versus preferable structures. Do you see the difference? Preferable is like where these elements want to be. Are they comfortable? In a valid structure, that's this. Everything is fulfilled. Everything is fine. The electrons are there. It fits, but it's not a preferable structure. And so maybe you're asking like, well, how do you know the difference? Here's how we know, okay? What I want us to do is I want us to look at an oxygen, a single oxygen atom. How many electrons did oxygen bring to the table? How many valence electrons did oxygen bring with it? 6. But let's count this. It has 1, 2, 3, 4, 5, 6, 7 electrons surrounding it. Like immediately close to it has 7 electrons, right? When we're looking at this, we're counting just the ones close to it. It has 8 if we're talking shared, but directly surrounding oxygen, it has 7 electrons. So it brought 6 to the table, but now it has 7, which means oxygen has a -1 charge. Right? It brings 6, but now it's surrounded by 7. Now, would that be the case for every oxygen in this structure?
Yes.
Yeah, it would, because each of our oxygens look the same. So what we have right now is an oxygen that's carrying a -1 charge. Every single one of our oxygens is doing that. But let's take a look at phosphorus. How many electrons did phosphorus bring to the table?
5.
It brought 5. 1, 2, 3, 4. So what charge does phosphorus have? A +1. A +1. Right? And so the reason this structure is not preferable is because every single one of our atoms is carrying a charge. And we want to have as few atoms as possible carrying a charge. That's the goal, is to have as few atoms as possible carrying a charge. Okay, so maybe we want to write that down in our notes. And I know this is kind of bouncing back and forth between our practice sheet and our note sheet, but we want as few atoms as possible carrying a charge. Okay, we want as few atoms as possible doing that. So here's our question. How can we fix it? How can we make this structure more favorable than it currently is? Do we have any thoughts about what we could do? I haven't really introduced this yet, so this is just us thinking outside the box, us being a little bit creative. How could we restructure this to make less stress essentially on our molecule? So I can't add them or take them away, but I can relocate them. Okay, and what I want us to do here is we're going to choose one of the oxygens and we're going to move its lone pair. I'm going to choose this one right here. Okay, this one right here. We're going to move its lone pair from a lone pair into a bond. Okay? And so by doing that, that removes the charge right there and the charge right there. Right? By doing that, now we're looking at a phosphorus that has 5 electrons surrounding it and an oxygen that has 6 electrons surrounding it. Right? And so by doing that, we're alleviating the stress basically on 2 of our atoms. Okay? Let me walk back one more thing. Maybe I forgot to mention this. As we were in this position right here, as we were still in this position, did you notice what does the sum of all those charges add up to be? -3, which is the charge on our molecule, right? That's what we want. Those individual charges have to add up to the charge of our molecule. But when we start working it forward, when we start working it like we were going to, we're going to take this lone pair, and we're going to move it into a bond right here. Now we've alleviated those extra charges, and now we still have a -1, -1, -1 that results in that -3 charge. So we're alleviating some stress off of those molecules. So let's kind of zoom in on it again. Here's phosphorus's 5 electrons that it brought to the table. Here's oxygen's 6 electrons that it brought to the table. And that's how we've alleviated those charges, okay? So I want you to kind of zoom in, right? Here was phosphorus's dot diagram individually. It kind of hinted to us that we either needed it to be a double bond or we needed it to be a lone pair. And in this case, it needed to be a double bond. Phosphorus is allowed to have more than 8 because it has the d orbitals available to it. Okay, so let's write ourselves a little reminder. Okay, it has the option or the ability to carry more than 8 electrons because it has the d orbitals. So that means any element in row 3 or below has the ability to have what we call an expanded octet. That's what it's called, an expanded octet. And an expanded octet means just that. We're able to have more than 8. So it's anything in aluminum, silicon, phosphorus, sulfur, chlorine, iron, any of those elements below that, because they're in the 3rd energy level. Anything after that has the d orbitals available, right? Because the 3 d orbitals is when they open up. Anything after that point has the ability to have more. Yeah, that's a great question. Great question.
Magnesium, sodium, and sodium included?
Yes, agreed.
Okay.
Those included as well. But since they're ionic, there'll be less sharing and more giving taking.
I see.
Yeah. Yep. Very good question. Anything else here that we want to think about or question about? That was a lot of information I threw you at one time, okay? Eventually, we're going to get to some more information with molecules like this about making the choice on oxygen and why did we choose that oxygen and things like that. We're going to talk about that in a little bit, but not today, okay? Let's move into this category down here, multiple bonds. We already dipped our toe into double bonds right here, which is what we want. Let me tell you that this bond, right, this is called a double bond. You can have single bonds, double bonds, or triple, but you cannot have quadruple bonds. So you can't put all your octet in bonds between 2 atoms. So you can have to go up to 3, but not more than that. Let's try the second one right here, HCN. Let's try HCN, okay? HCN. So let's count up our valence electrons. One plus 4 plus 5 gives me 10 electrons total. What's my central atom going to be here?
Carbon.
Carbon. And then I'm just going to surround it with nitrogen and hydrogen. I will bond. That uses up 4, so I've got 6 electrons left. Am I going to put lone pairs over here on hydrogen?
No.
No, we're not going to, because we know better, okay? But I could, right? Our rule is kind of outer to in, right? Outer to in. So I might put them here and then see what problems I run into, Okay, so at least right now, I've got all my Lewis structures, I've got all my electrons on the image, right? I don't have any Lewis, my goodness, I can't speak. I don't have any electrons left to put on. But I see an issue with this structure. Do you guys agree? What issue are we seeing?
Carbon doesn't have enough.
Carbon does not have enough, right? It does not have a complete octet. So now we've got to start moving electrons around. We've got to move electrons around. So what do we think here? Can we move this lone pair into a bond? Would that help? Yeah, it would. Okay, so we're going to take this lone pair and we're going to move it to a bond. And we've got now carbon to be at 6 and nitrogen to be at 8, so that's no good yet. What should we do now? Can we do it again? Move another lone pair. I can move another lone pair into a bond. And now I think I've got complete octets. I didn't add electrons, I just slid them over. Okay, I want you to look at it another way. Hydrogen had 1 electron, carbon had 4, nitrogen had 5, right? We're bonding, 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 right? That's really what we're seeing here. I don't think it's time efficient to draw out the individual dots every time, but it does give us a visual for what actually happened, right? We didn't actually move a lone pair from here to here, right? But for time's sake, maybe that's what we do, but that's not actually what's happening. Are we all good with that? I don't ever draw out individual dot structures, but I do think it's important for you to see that those things are actually happening, right? Those single electrons are forming bonds by sharing. So tell me about preferences here. Carbon has 4 bonds, it looks like. Does that make carbon happy? Where is it? Carbon wants 4 bonds. What about nitrogen? It wants 3 bonds and 1 lone pair, which it has, right? So everybody's happy. Any formal charges here? Do we have any atoms that are carrying charges that they shouldn't be? Right? Because carbon brought 4 to the table, so there's carbon's 4. Nitrogen brought 5. 1, 2, 3, 4, 5. So I think we should feel pretty good about that. Agreed?